So this next section might seem like it kind of sticks out a bit because it's not quite dealing with matrices. However, it is dealing with systems of linear equations. So this next topic is about partial fractions. The main idea is we are so used to condensing fractions. So adding a bunch of fractions together or rational expressions and making it a single fraction. What we want to do is we want to find the process to reverse it. And that's what partial fraction does. It takes a condensed, proper rational function, proper being the key word. So proper means the degree of the numerator is smaller than the degree of the denominator. And it turns it into its expanded form. So we're figuring out what we had to add together to get that condensed fraction. So the process is very similar. It just depends on the factors that you have in the bottom. So really to go through this, I'm just going to do a ton of different examples and show you how to set up the process. So we're going to find the partial fraction decomposition, which we're going to abbreviate PFD, of this particular rational function. Okay. So again, the idea is I want to see what fractions did I add together so that it's simplified to this expression. And the first thing I need to always do is I need to check to make sure it is proper. If I look at the degree of my numerator, it's 1. The degree of my denominator is 2. So the degree of the numerator is less than the degree of the denominator. So this is good. This is proper. If they are the same degree, that is not proper. You have to go through division to turn it into proper. So with this, it's going to be much easier if I look at that bottom as a factored form. So if I take x squared plus x minus 2, those first terms have to multiply to x squared, so an x and an x. And the only way to get to negative 2 is a 2 and a 1. 1 being positive, the other being negative. So if I do positive 2x, that gives me an inner of 2x, outer minus x, condenses to the right thing. Okay. So this is what my fraction, my two fractions added together shrunk to. I have two factors in the bottom. So each factor is going to get its own fraction. So this will split and I'll have one fraction plus a second. One of the factors is going to be x plus 2. The other is x minus 1. Because when I go to add these two together, these have a common denominator of exactly x plus 2, x minus 1. So I would add them together to be able to get that denominator. The problem is I have absolutely no idea what to put in the top, so that when I go ahead and multiply this by x plus 1 over x plus 1, and this by, x minus 1 over x minus 1, and this by x plus 2 over x plus 2, that whatever is in the top will condense to x plus 5. However, I do know that because this is a proper rational expression, the numerators of these things should also be proper. So this is a first degree polynomial in the top, or in the bottom, which means we should have proper, we should have a 0 degree polynomial in the numerator. Same thing here, first degree polynomial, to keep it proper, you get 0, which is a constant. So both of these should be constants to keep the fractions proper. Okay. So again, this is my setup. If I go ahead and add these two things together, it would condense into this fraction. But I need to figure out what do I put in place of A and B, what numbers. Okay. So now we need to figure out those values. So what I'm going to do is I'm going to make my life easier. I need to solve for a and b. Let's go ahead and wipe these fractions. So I'm going to multiply through by my common denominator to get rid of the fractions. So we're going to multiply the equation by x plus 2 and x minus 1 to wipe the fractions. Okay. So again, what I currently have is x plus 5 divided by x plus 2, x minus 1 is broken down, 2 factors in the bottom. I have 2 fractions. Each factor gets its own denominator. I keep wanting to put plus 1 there. And then to keep this proper, first degree polynomials in the bottom should get 0 degree in the top. And now I want to take this whole thing and I want to multiply by x plus 2, x minus 1. In doing so, that would make those cancel on the left-hand side, and we would just get x plus 5. Over here, when I multiply this expression by both of these, just the x plus 2 cancels. So I'm left with a and x minus 1. And then over here, the x minus 1's cancel, so I'm left with b and x plus 2. So there are going to be many different ways that you can go about solving these. We can do something called matching coefficients, or we can go ahead and we can also just find values to plug in for x, because this equation should be true for all of your values, okay? So I tend to like that method a lot better, but when we have more complicated things, the matching coefficients tends to be really helpful. Okay, so here I'm going to plug in values of x to find a and b. And the easiest ones to plug in are, well, if I plug in 1, that will make this 0 and a will disappear. So I'm going to plug in x equals 1. So anywhere I see an x is going to get replaced by 1. So that gives me 1 plus 5 is equal to a times 1 minus 1 plus b times 1 plus 2. Well, that gives me 6 on the left. A is completely gone, which is great. No longer need this piece. And then we have 3 times b. So dividing through by 2 or by 3 gives me b has to equal 2. So that's what one of my coefficients will have to be. This needs to be replaced by a 2. Then if I pick another value of x, I can solve for a. So in this case, plugging in -2 would also be good. So on the left-hand side, that gives us -2 plus 5. A times -2 minus 1, and b times -2 plus 2. So again, this is great because that will disappear. You get 0b. So this will be +3 is equal to -3a. So our value of a is -1. So these are the 2 constants we need for our partial fraction decomposition. This rational expression can be broken down into a, which is -1 over x plus 2, plus b over x minus 1. Okay. So again, you can definitely check your answer. You can go ahead and add these 2 fractions together, and you should see you get the expression over here. What I do want to also show you is the other method, which is how to match coefficients, and you still will get the same results here. Again, I don't care the method that you use for this. It is completely up to you. So I'm going to go ahead and I'm going to delete all of this and show you that second method. Okay, so method 2 is we can match coefficients. So what I'm going to do is I'm going to expand everything out. This gives me a times x minus a, b times x plus 2b. Then I'm going to group those like pieces. So these are my things that involve x. So grouping those, I have a plus b times x. And then I look at those constants. We have minus a plus 2b. So those get grouped together. So I can go ahead and move that over a little bit and say it's the same as adding these. So now matching coefficients, we look at the x term, and then we look at the constants. Those are the two things we have. On the left-hand side, if I look at my x's, I have 1, and then I have a plus b over here. So that tells me 1 should equal a plus b. Then looking at my constants, we have 5, and then that's the constant on that side. So 5 should equal negative a plus 2b. So you end up with a system of equations that you would have to solve. But thankfully, this is a system we can use elimination on, because we have positive a and negative a. So if I go ahead and add these two together, the a's just cancel, and that gives me 6 is equal to 3b, and you find out b is still going to be 2. And then once you know b, you plug it back in. 1 should equal a plus b, but b is equal to 2. So negative 1 is our value of a. So we still get exactly the same thing. This rational expression is equal to a over x plus 2 plus b over x minus 1. So this is our partial fraction decomposition. Okay. Again, I don't care which method you use. You can also use combinations of these. Perfectly fine for you to do, okay? But this is our process that we're going to go through. Again, I like the first one of just plugging in values. I think it's a lot simpler. Doesn't always work for us. It just depends on the problem itself, but we'll see ways that we can kind of combat that. So you still are going to have to know how to solve systems of equations. So ultimately, we're going to consider 4 different cases. The first case is exactly what we just experienced. The denominator is a product of linear factors, and there's absolutely no repeats, okay? So let's find the partial fraction decomposition of this expression. And again, it is proper because the degree in the top is smaller than the degree in the bottom. So first, I need to figure out what factors are in the bottom, so I have to factor it completely. Well, I can take out an x, and that leaves me with x squared minus 1. And then that I can factor further. We have x, x plus 1, and x minus 1. So ultimately here we have 3 different factors in the bottom. So that's going to equate in our decomposition to 3 fractions in the decomposition. Okay. Our factors are x plus 1, and x minus 1. And that is first degree in the bottom. So to keep these proper, all of these numerators are going to be constants, a, b, and c. So when you have linear in the bottom, linear terms get constants in the numerator. That is 1 degree less. Okay. Now I want to wipe my fractions to make this easier. So we multiply by our 3 factors. So we multiply by x, x plus 1, and x minus 1 to wipe my fractions. Okay. And so over here, when you multiply by all 3 factors, you're just left with the thing in the numerator. When I multiply this by all of these, the x's cancel. So you're left with the numerator and the 2 factors you didn't have. For the second one, we're left with the numerator and the x plus 1 disappears. So we're left with x and x minus 1. And for the third, the x minus 1 cancels. So we're left with c, x, and x plus 1. Okay. So again, I think it's much easier to just plug in values. This should hold true for all values of x. So I'm going to start just picking numbers that work. Well, if I plug in 0, that will make both of these disappear. So if I do that on the left-hand side, we get 0 squared plus 2 times 0 minus 1. And this is the only one I'm going to plug in 0 in for everything. You get a times 0 plus 1, 0 minus 1, b times 0 minus 1, c times 0 plus 1. So again, when you times by 0, those do not matter, so they are gone. So on the left-hand side, we're just left with -1, and over here we have a times 1 times -1. So -1 is equal to -a, telling us our value of a is +1. Okay. Now I want to do the same thing. Another value that's really good to pick is -1, because then this will disappear and this will disappear. And so now I'm going to plug in -1. -1 squared is +1. 2 times -1 is -2, and then -1. And then I know when I plug in -1, this is gone, -1, this is gone. We're just getting b. So we'll have b times -1, and then -1 is -2. So over here, that simplification is -2, and that leads us to 2b. So our value of b is -1. Okay. And then I have one last number to find. I've used 0, I've used -1. Now it's going to make sense to use +1, because then this is gone and this is gone. So you're really just using those numbers that cause you an issue in the denominator. Okay. So if I plug in 1, that gives me 1 plus 2 minus 1. Then we're just going to have c times 1 times 2. So this tells us 2 is equal to 2c, giving us c is +1. Okay. So our partial fraction decomposition, to just zoom out to get it all the way back up here, is we started with x squared plus 2x minus 1 over x times x plus 1, x minus 1. We get a over x. Then we have b over x plus 1 and c over x minus 1. So again, if you were to go ahead and add these three things together, you would see you get exactly what is on the left. So again, it is reversing that process because we are so used to adding these and getting this expression, but we're doing the exact opposite. Okay. Our next two cases are a little bit more complicated. And then the third one is extra complicated that you're going to see. We just do a setup for. We definitely cannot solve that thing. But this is going to be when we start to have repeat factors. So case 2 is the denominator is a product of linear factors. Some can be repeated, or maybe multiple are repeated. But to give you an example of this, if I look here, this factor of x minus 2 squared is a repeated linear factor. Okay. Now, technically, you have two different ways that you can set it up, but one of them is definitely much more preferred than the other, and it's the one that we're going to utilize. But just to show you that this does work, I'm going to show you my first setup. So it follows the same approach. We have x squared minus 5x plus 16 over 2x plus 1 times x minus 2 squared. The way you can think of this is you only have two unique terms. So you break it down into two fractions. The 2x plus 1 is one of them, and then the other term is x minus 2 squared. This is linear, so it gets a constant above it. But over here, that's a second degree. So to keep it proper, it would be one less. So a second degree gets a first degree or a linear top. So in that case, I have something times x plus a constant. Okay. So that gives me first x to the first and then x to the 0, all the terms down. If this was cubed, well, then you would need something times x squared, something times x, and a constant. So you would have bx squared plus cx plus d in the top. But that would be a lot, okay? The problem is this is not really nice. So it's not something we tend to like to do. So essentially, if you're going to go on to Calc 2, you're going to learn a process there called integration. And this is going to be messy to deal with as opposed to a nicer breakdown of terms. And this is even harder to go through and deal with. So the second setup is the one that we prefer. So I still have my same piece here. But instead of thinking this as two factors, you have one and two more. So you really have three. So we're going to have three fractions. Okay. So ultimately, what we do is we still keep the 2x plus 1 with a linear above it. But I'm going to build up to having two of them. So we start with the repeated linear at the first power. And then you keep increasing it until you hit the end power. Then this is nice. You're considering it to just be a linear term, so you get constants in all of the tops. So each fraction is treated like it has a linear denominator. So again, I start with the repeated term to the first power, and then I bump it up until I hit the actual power. If this was to the third, I then would have 3 of this factor and 1 of that, so I would need a third fraction, and you would just bump it up and you'd have 3 fractions dealing with x minus 2 to a power. And then again, these are treated now like linear terms, so they just get b and c above it, okay? So this one is much easier because when you get to Calc 2, again, dealing with integration of this will be nicer than this expression, okay? So we like the simplified version. But now from here, it's exactly the same process. So we're going to go through and we're going to go ahead and wipe the fractions by multiplying by that common denominator. So on the left-hand side, we are only left with the numerator. On the right-hand side, this first fraction, the 2x plus 1 is gone. So we'd have a times x minus 2 squared. When I go to multiply the second, one of them cancels and leaves with 1. So I'd have b times 2x plus 1 times x minus 2. And then the third fraction, both cancel, and we're left with c and 2x plus 1, okay? So again, I want to pick numbers that I'm able to easily see what they are. So the first number that's pretty clear to me is plugging in 2, because those will both disappear. So if I plug in 2, that would give me 4 minus 10 plus 16. And then on the right-hand side, I'm just going to be left with c, and that gives me 2 times 2, which is 4, plus 1. So 4 plus 16 is 20, minus 10 is 10, and that's equal to 5c. So immediately we have our value of c is 2. Okay, so that gives me one of my constants. Another I technically could plug in is -1/2, because that would make both of these disappear. But then I run out of options from that, and I sure don't want to plug -1/2 into this. That's going to be some messy fractions. So now that we know one of the coefficients, we're going to utilize that to our advantage. I don't want to plug in a fraction. Instead, let's just pick nicer numbers. Okay, so we could plug in -2, -1/2. To solve for a. But the fractions would be really messy. Okay. So instead, let's pick better values, or easier values to work with. So I'm missing 2 variables. So I'm gonna have to pick 2 values of x. The first value that I think is super easy to pick is definitely 0. Anytime we can plug in 0, fantastic. So over here, those would both disappear, and we're left with 16. Then we get a times -2 squared. We have b times 1 and -2, and then c times 1. Okay. So this gives us 16 is equal to 4a minus 2b plus c, but we know our value of c. It's 2. Okay. So this is just an equation involving a and b, so I'm going to go ahead and move the 2 to the other side to give me 14 is equal to 4a minus 2b. Okay. And then I could simplify this a little bit more if you want to. You don't have to, but you get one equation with 2 unknowns. I'm going to have to do a second. I do think it's easier. Everything's divisible by 2, so go ahead and divide it by 2. So this gives me one equation with 2 unknowns. So I need a second equation, so I'm going to pick a second nice number that I haven't used. I like to avoid minus signs because I can't tell you how often I also drop minus signs. So I'm going to pick +1. Okay. So plugging +1 in way back up here, that gives me 1 minus 5 plus 16. We have a, 1 minus 2 is -1. B, 2 plus 1 is 3. And 1 minus 2 is -1. And then C, 2 plus 1 gives me 3. So condensing this, that's 17 minus 5. This is 12. That's A minus 3B. And then remember our value of C is 2. So 2 times 3 is going to give us 6. So subtracting the 6 gives us 6 is equal to A minus 3B. So I have 2 equations and 2 unknowns. I now need to solve the resulting equation, or resulting system. You can use whatever method you want, elimination, substitution, and matrix. Completely up to you. So I'm going to start just by copying my 2 equations down. And you can solve this doing whatever method you want. I like elimination, so I can multiply this by -2 to make my a's cancel. So that gives me the first equation completely untouched. When I multiply by -2, that's -12 equals -2a plus 6b. And then we go ahead and combine these, and that makes our a's cancel. So 7 minus 12 gives me -5, and then minus b plus 6b gives me 5b. So immediately that tells me my value of b is -1. And now that we know our value of b, we can use either equation to solve for a. I think the second equation is nicer because I don't have to do anything in front of a. So our value of b is -1. So 6 is equal to a plus 3, which gives us a needs to equal 3. Okay. So this was our partial fraction decomposition all the way back up here. But now I know each of these values. A is 3. B is -1. And then our value of c, we solved back up there. That is 2. All right. So just be careful of your minus signs. In this case, you absolutely can put that minus sign out front because that's the only thing in the numerator. But you're going to see in our next example, when you have a quadratic in the top, if the minus is attached to the x, you can't just put the minus out front. Because if I had minus, say, x minus 5 over something, that would distribute to both of them, okay? So just be conscientious of your minus signs. So our third case we're going to actually solve a decomposition for is when the denominator contains irreducible quadratic factors with no repeats. Irreducible basically meaning you can't factor it, okay? So starting with this expression, I can factor that denominator a bit, and I am good. This is a proper expression. In the bottom, I can go ahead and I can take out an x, and that leaves me with x squared plus 3. That cannot factor anymore. It's only when you have x squared minus a perfect square. So that is stuck. So I have 2 factors in the bottom, meaning I'm going to have 2 fractions. Each factor gets its own fraction. Okay. My first term is still linear, so that means it gets a constant or just a number up top. So we plug in a. This, however, is a quadratic or second degree. So 1 less than that means it gets a linear term up top. So linear means we have something times x plus a constant. So my 3 unknowns are a, b, and c. Okay. So again, I need to wipe my fractions. So I go ahead and multiply through by that common denominator. The left-hand side just gives me the numerator. And then on the right-hand side, a will be multiplied by x squared plus 3. And then be careful here because it's this entire numerator times x. So you get the entire numerator times that last factor. So say this was x minus 1 here, this would be x minus 1, this would be x minus 1. You'd have to be careful with your parentheses. It's the entire numerator. Okay. So again, I want to see if I can plug in a value of x to immediately find one of my coefficients. Fantastic. And so 0 is definitely going to be a great one to plug in. So we'll start by doing that. On the left-hand side, that gives me 6. On the right-hand side, that gives me 0 plus 3. And this would be b times 0 plus c times 0. It would be even nicer if this was, say, something like x minus 1, because if I plugged in 0, that would just get rid of b and not c. However, in this case, it does get rid of this entire piece. So that tells me 6 is equal to 3a, and so I do solve for one of my coefficients. A must equal 2. Okay. And now again, I can totally go through and I can plug in a different value of x, say 1 and then 2, and get that system of equations. But my other method is going to be to match my coefficients. So I want to get some practice with that, okay? So going back up here, I know x squared minus x plus 6 is going to equal a, which I now know is 2. Okay. So distributing stuff out, that's x squared minus x plus 6. That's 2x squared plus 6. And then distributing the x gives me bx squared plus cx, okay? Now at this stage, you could group stuff together, but I'm gonna leave just my unknowns on this side. So I'm gonna move these over. So we'll go ahead and subtract 2x squared. And then we'll also go ahead and subtract 6. At least in this case, this is nice. Those are completely gone. That disappears. X squared minus 2x squared leaves us with negative x squared minus x. And that must equal bx squared plus cx. So from here, I'm going to go ahead and equate those coefficients. So we're going to equate the coefficients of x squared. On the left-hand side, we have negative x squared. The only thing dealing with x on this side is b. So immediately that tells me -1 has to be b. I should use the same color that I've been boxing all of these in. And then I do the same thing with the x terms. So we go ahead and equate the coefficients of x. So on the left-hand side, I've got -1. On the right-hand side, I have c. So immediately that tells me that -1 is also my value of c. So I have all 3 of my unknowns. So now I can write my decomposition. So I'm just going to go ahead and copy this from down here and show you how you have to be careful about writing this. So my value of A, we figured out, is 2. B's value is -1, and so is C's value. Leaving it like this, perfectly fine. Another way you could write this is you can go ahead and break it down, because remember, we can split a numerator. So we can write this as -x over x squared plus 3 and -1 over x squared plus 3, okay? And in that case, now you have a single term in the top. You have no problem then just making this minus. The number one mistake I see is this. If you have -x minus 1 in the top and x squared plus 3, say I'm adding these together, this is not the same as pulling that minus sign out from that first term and not doing it from the second, okay? Because again, this is multiplication. This would distribute back in, right? So instead, you would have to pull this out and it would turn that to positive. Those are equal to each other. So just be very, very conscious of your minus signs, okay? But any of these is an acceptable form for that partial fraction decomposition. Now our very last case is like the linear, but now those quadratic factors could repeat. That would be absolutely atrocious to actually solve one of these. So I'm just going to give you an example of how to write out the form. So here we have a linear factor, and then we have this quadratic, which is repeated, and x squared plus 4 cannot factor. So we do exactly the same thing. This is one factor. You have 3 of these. So you're going to have 4 fractions. Okay. Your first factor is x plus 1. That's first degree. So it gets a constant. Then we do the same thing where we build up. You start with that factor to the first power, then that factor to the second, and you keep going until you reach the actual power, which is the third. Okay. So you start with it to the first, But then from here, you're considering this to be a quadratic that's repeated. So each numerator gets a first degree. Okay. So you got to do your variables in order. You need an x and a constant. So here that would be bx plus c. So going in order a, b, c. Then I get a linear up here. So my next variable would be dx plus e. And then fx plus g. Okay. So you can see that would be absolutely messy because we have 1, 2, 3, 4, 5, 6, 7 unknowns that you'd have to solve for. And that would take a lot of algebra to do. Okay. Again, just the setup for that one, we're not going to go through actually solving it, but this would be how we set up that decomposition.